Hello everyone. In this lecture, I will talk about properties of biomaterials. In the previous lecture, we discussed basic concepts of biomaterials, their classification, and some basic properties and applications of those biomaterials. Before talking about properties of biomaterials, I will talk about different terms or different aspects which are related to biomaterials. Talking about the journey of biomaterials from laboratory to clinics, there are different studies or different things which need to be studied properly for the biomaterial to come to the clinical settings. So there are three phases in the development of biomaterials. First is the development or synthesis of the biomaterial. After the development and synthesis of biomaterial, the biomaterial should be thoroughly tested in the preclinical studies, and after the preclinical studies it should pass the clinical studies, and after that there should be the regulatory approval. There should be the approval of the ethics committee and regulatory committee, and after that there will be the approval to and after that approval will be given for the commercialization and clinical application. First aspect that we need to study is the toxicology. A biomaterial should not be toxic unless it is specifically engineered for such requirements. E.g., a drug, for example, a drug delivery system is that targets the cancer cells and destroys them. In that case, the biomaterial system should be toxic. But in all other cases, the biomaterial system should not be toxic, and toxicology studies must be done before getting them into the clinics. Some of the examples of the toxicology studies of the polymers. In case of polymers, which have the low molecular weight, some of the some of the monomers may leach from the polymer, and they may lead to toxicity. And all these monomers or leachable substances should be studied. Another important aspect is the biocompatibility. Biocompatibility means that the material should not be harmful or should not elicit any untoward or harmful response in the body or cells. Biocompatibility studies are very important uh, for these regulatory and ethical approvals. Third aspect is the study of the pathobiology or functional tissue structure. As these medical devices are ultimately meant to be implanted in the physiological conditions, these biomaterials should be compatible with each pathobiological condition. For this, fundamental mechanism of disease processes should be known. The pathobiology of the disease in which these biomaterials are to be incorporated should be known. For the effectiveness of these biomaterials. Next one is foreign body reaction. When some foreign material is implanted or injected into the body, it leads to the foreign body reaction. The foreign body reaction with the different biomaterials and in different disease conditions should be studied thoroughly. This anatomical site of implantation is also important as it determines the requirement of geometry, size, mechanical properties, and bioresorption of the biomaterial. So the design of material should be compatible or should be according to the anatomical site of implantation. For example, like if we use materials for intraocular lenses, for hip replacement, for heart valve, different materials and different shape and size are required according to anatomical site. So the study of anatomical site of implantation is also important before the synthesis or before making the medical devices from these biomaterials. And each biomaterial or each medical device should have the optimum mechanical performance or mechanical strength so that it performs well in the physiological condition according to the need. So for this mechanical performance, mechanical durability, bulk properties, and surface properties of the material are studied thoroughly. So for the ethical approvals and regulations, all the regulations should be met, and ethical approvals or regulations should be defended with these different types of tests to make these life-sustaining devices. Now talking about properties of biomaterial. In each biomaterial, there are two portions, or one is the surface portion, one is the bulk portion. So properties that come from this surface or surface atoms are called surface properties, and the properties which are because of the bulk atoms are called bulk properties. Both these surface atoms on the surface and bulk atoms, they have different interaction with outside environment or outside tissue. So surface properties will always be different from these bulk properties in most of the cases. And these bulk and surface properties have been shown to directly influence or control the dynamic interaction with the tissue or implant. So these surface or bulk properties, they directly influence the interaction with, or they directly influence the outcome or interaction with the tissue. So for the biomaterial, it is critical to study both these bulk properties and surface properties. And also these bulk and surface properties, they may change over time in vivo condition. For example, a biomaterial implant is implanted. It is surface properties and bulk properties. It may change over time after sometime when they are implanted. So overall study of these surface and bulk properties uh, over the whole life of these biomaterials. If I can give the example, for example, in cardiovascular grafts, when the blood flows through these grafts, different types of cells from the blood, they interact on the surface, and the surface properties are changed because now the layer of cells are on the surface. So the study of these bulk and surface properties are very important for the implant. First of all, we will start with the bulk properties. Bulk properties are mostly studied for the solid states only. As solid states are distinguished from other states of the matter by the fact that their constituent atoms are held together by a strong interatomic attraction. So atoms in the bulk will remain always in the bulk, and atoms on the surface will remain always in the surface. Whereas in case of liquids, the atoms in the bulk may move to the surface and atoms in the surface may move to the bulk. So the bulk properties are usually studied for the solid state of the matter. The electronic structure and almost all the properties of the materials depend on the nature and strength of the interatomic bonds. To study the study of these interatomic bonds can be done by the classical theory, and classical theory states that there are primary three bonds in the solid state. Uh, these are ionic bonds, covalent bonds, and metallic bonds. By the help of these bonds, there is a three-dimensional arrangement of atoms or ions in a solid. And this three-dimensional arrangement of atoms or molecules in a solid state lead to the formation of crystal. A crystal is a solid whose atoms or ions are arranged in an orderly repeating pattern in a three-dimensional fashion. Each crystal is made up of the repeating elements or subdivisions, which is called a unit cell. There are different types of unit cells, for example, simple cubic unit cell, face-centered cubic, body-centered cubic, and hexagonal closed packing unit cell. Each unit cell of a crystal have the same properties as of the whole crystal. So a crystal is made up of different types, large number of unit cells. Or we can also say that a model of a whole crystal can be generated by simply stacking up unit cells like blocks or hexagonal tiles. In the next slide, we will have the look of different types of unit cells in a diagram. Talking about different types of unit cell, in the simple cubic unit cell, the atoms are placed in the corners of the cube. For example, in this cube, the 8 atoms are placed in the corners. So it is a simple cubic unit cell. So this is the one unit cell, and this is the whole crystal, and it is made up of different types of unit cell. This one unit cell, 2 unit, 3 unit cells, and large number of unit cells. In a body-centered unit cell, the atoms are placed in the corners of the cube like this, and also one atom is in the center of the or center or body of this unit cell. So it is called body-centered cubic. So this is the whole crystal of the body-centered cubic, and this is the one unit cell. And in case of face-centered cubic, the atoms are placed, 8 atoms are placed in the corners of the face-centered cubic, and atoms are also in the faces or sides of the cube. For example, if this is a side, so if this is a one side, this is a one side, so one atom is also embedded here, and one also is embedded here. So there are 6 faces of the cuboid. So there are 6 atoms in the in the faces or walls also. So that's why it's called face-centered cubic structure. And in the hexagonal cubic, there is a hexagonal structure like this. You can see in this figure. If I can talk about one unit cell, the atoms, 6 atoms are placed in the corners of the hexagon, and 6 atoms in the bottom of this unit cell. One atom is above in the upper face, and one atom is in the lower face of this unit cell, and 3 atoms are between this upper and lower layer. So all the arrangement of atoms in a space in different orientations lead to the formation of different types of unit cells, and these different types of unit cells will lead to formation of different crystals, which each crystal have some unique properties, surface and bulk properties also. So as I already talked about, different properties of materials come from different types of unit cells they contain, or different types of crystals, and also it depends on different types of bonds that are present in the material. So there are 2 types of bonds, one are the strong bonds and another of the weak bonds that can be present in the material. In the strong bonds, there are ionic bonds, covalent bonds, and metallic bonds. In the weak bonds, van der Waals bonds and hydrogen bonds may be present in the material. In the ionic bond, there may be electrostatic interaction. One atom is electron donor and one atom is electron acceptor. For example, in case of sodium, there is a one extra electron. In case of chlorine, there is one electron is less to complete the valence shell. So this donor atom gives the one atom to this atom, and it is the acceptor atom, and they form the ionic bond, and which is a very strong bond. And after forming this ionic bond, one atom is a donor, it forms the cation, and the atom which receives the electron, it forms the anion. And thus they are strongly yeah, attracted by electrostatic or Columbus electrostatic attraction. In case of some ionic solids, in case of some ionic solids, the cation, it is in some cases it is surrounded by many anions to possibly reduce the strong repulsion by the different cation. In such ionic solids, no discrete molecule exists. All the in the crystal structure, all the ions and cations, they are arranged in a crystal structure containing one cation in the center and anions surround it, uh, and it leads to the highly ordered structure of the crystal. And in case of face-centered cubic, body-centered cubic, or hexagonal close packing, in that case also the ionic interactions may occur in those crystals. Since in these ionic crystals there is no electron which is loosely bound, actually the electrons which were free, they now were involved in formation of ionic bonds. So these ionic solids, they are actually poor conductors of electricity. And also in case of ionic solids, because of the close packing, of the cations and anions surround it. It leads to the low energy state. Thus, these molecules also have the low chemical reactivity. Examples in the ionic solids are sodium chloride, magnesium oxide. That's true. The elements which form the covalent bond, they fall along the boundary between the metals and non-metals, such as carbon, silicon. Yeah, such as carbon have the four valence electrons, and they have the equal tendency to donate and accept these four electrons. Thus, they do not donate these electrons; they actually share these electrons with another carbon atoms or another other atoms. So, the sharing of these electrons will lead to the formation of covalent bonds. So, because of the sharing of these electrons by the atom, this leads to the formation of attraction between the two atoms, and this bond is, because of the sharing of electrons, is called covalent bond. If I take the example of carbon, here for example, carbon, it has four valence electrons. So there are four electrons missing to form the complete valence shell. So it takes it shares these four electrons with other four carbon atoms or hydrogen atoms. So if we take here hydrogen, another hydrogen here, another hydrogen here. Hydrogen also has a one valence electron. So it shares these electrons with this, and it and all the four and all the eight electrons in the valence shell are completed by sharing these electrons. So this bond here, these are the covalent bonds. So between the carbon, carbon or carbon hydrogen, covalent bonds are formed. Again, the sharing of electrons or localization of these valence electrons renders the material poor conductors of electricity because all the electrons are now shared or bound by this covalent bond. In case of different crystals also, hydrogen bonds also exist in case of different crystals. For example, in diamond and silicon, the crystals in diamond and silicon, the bonds between the carbon-carbon atoms are covalent bonds. Metallic bond is also a very strong type of bond which occurs in metals, and because of this bond, metals are very strong and have very high melting temperature because of this strong interatomic attraction between the atoms. In metals, as you can see in this figure, like zinc or sodium, there is a metallic core which is a positive ionic metallic core is there, and atoms and the negative electrons like a gas, they circulate between these atoms, and these negative charge electrons, they act as a glue between these metallic cations. So this interaction leads to the formation of metallic bonds and metals are formed. So this strong bond between there's a very strong bond between these cations, metallic cations and electrons. And the more these metallic core, the more it is tightly packed, the more there is a strong attraction between these metallic cations, and it forms a more packed crystal structure. As these electrons between these cations, they are free. They are not particularly. They are not attached. They are like they act as a glue, but they are free. They are not attached to this metallic core. So they act as a glue, but they can move around in this metallic core. Thus these metals are high. They have high electrical and thermal conductivity. In addition to these strong bonds, which are mostly present in different materials, there are also weak secondary bonds that also significantly influence the properties of the materials. So in case of van der Waals, force of attraction or van der Waals bonds, This type of attraction is allostatic attraction between the atoms. For example, if the atom A and atom B has different densities of positive and negative charge. For example, this is a in this portion there is a high positive charge in this atom, and in this portion there is a high negative charge. And also opposite, there is high positive charge in this side and negative charge in this side. So from this positive and negative charge, these atoms will attract to each other, and this leads to the van der Waals bond or van der Waals attraction. Now talking about hydrogen bonding. Hydrogen bonding is also a type of allostatic attraction. It occurs between the hydrogen atom, which is bound to some electronegative group. Because of bonding to the electronegative group, this hydrogen atom, it attains some small positive charge, and because of that, because of its attaching to electronegative group, and then it attached to another atom which is a small negative delta negative charge, which are in that in other side. So it forms a hydrogen bond. Some of the electronegative atoms like oxygen, nitrogen, fluorine, which are attached to the hydrogen, and they form this hydrogen bonding. This hydrogen bond can be of two types. For example, intramolecular hydrogen bond or intramolecular hydrogen bond. In the intermolecular hydrogen bond occurs between the separate molecules, and this intermolecular hydrogen bond occurs between the separate molecules, and intramolecular hydrogen bond occurs in the same molecule, in the different parts of the same molecule. So this was about different properties of the material, or because of this because of the different types of bonds that are present in that material, and they influence the properties of the material, and they also influence the interaction of these materials with different in the physiological system. So materials are divided into three major types: metallics, metals, ceramics, and polymers. All these types are based on different types of bonds and composition of the material. So talking about metals are the substances that exhibit metallic bond in the solid state, and these are called metals. And 85% of these metals show the crystal structure. And the common crystal structures in the metals are face-centered cubic, body-centered cubic, and hexagonal-centered cubic structures. Hexagonal-centered cubic, these unit cells are present in case of metals. So in case of face-centered cubic and hexagonal close packing, 74% of the volume is occupied by these spheres or atoms in each crystal. This is the closest possible packing. Face-centered cubic and hexagonal centered. In FCC and hexagonal packing, every atom or ion is surrounded by the 12 touching neighbors or 12 touching these spheres. In case of body-centered cubic, the occupied space which occupies which the space occupy is 64% and 68%, sorry, and rest of the space is empty in the crystal. Here is the typical metal crystal structure. I think this is the face-centered cubic structure, where there are 8 spheres or atoms in the corners, and 6 are present in the faces. So this is the one unit cell of the metal which later forms the crystal. Now talking about ceramics are usually solid inorganic compounds with various combinations of ionic and covalent bonding. Ceramics often have the more complex structure, and they also have the tightly packed structure and tightly packed these atoms. These ceramics, they have different properties from the metals. They are extremely hard. By the way, metals are also hard, but they have some different properties. Like They are corrosion resistant, whereas metals usually corrode. They are heat resistant. They have low electrical thermal conductivity. They are poor thermal shock. They have the thermal shock resistance. So they have very different properties from the metals. So, and they are also mostly used as materials for various implants. They also has a high wear resistance and extreme hardness that can reduce wear caused by the friction. Carbon is often included in the ceramics, even though it is not a compound. And also it has a different properties from ceramics, like it conducts electrons, it conducts electricity in the form of graphite. As you may be knowing that carbon has a two crystal structures. In diamond it has a tetrahedral coordination, and in graphite is a hexagonal arrangement of the atom. So from this example, you can also know that a different orientation of atoms or different crystal structures uh, can lead to the different properties of the material. Even the material is same, but different crystal structures or different orientation of atoms can lead to different properties and different mechanical and other properties. And there may be also the difference in interaction of these materials with the biological system. Now talking about polymers, in the polymers, the constituent atoms of the polymers are usually carbon atoms, and they are joined by the linear chain-like structure by a covalent bonding. And these chain-like structures, they could be the straight chain or branched chain-like structures. Atoms in these chains are attached by the covalent bonds, but these chains, adjacent different chains in the polymer, they can also be attached by van der Waals force of attraction or hydrogen bonding. So because of this van der Waals force of attraction hydrogen bonding, these polymers are comparatively weaker materials as compared to ceramics and metals. These polymers have also been used in biomaterial science and tissue engineering applications for the delivery of different bioactive molecules and drugs in the physiological condition. There is also another type of materials which are called composites. Composites are the materials which are formed by the formed by the combination of different types of materials. For example, they have the properties of both metal, ceramics, or they can have properties of all the three types of these materials, or two types of these materials. So they are called composites. And also when for example, if the composite is formed from metals and polymers, they have the different properties from metals and different properties from polymers, which is in between. So composites are also advantageous in case of different tissue engineering applications, or in case of different biomaterial devices. This is all about this lecture. In the next lecture, we will study more about these biomaterials and different mechanical properties of these biomaterials, and how these mechanical properties are studied. We will discuss in next lectures. Thank you everyone for your attention.